Welcome to the lesson on the concept of moles.
So, what is a mole? A mole is the quantity of a substance having the same number of atoms found in 12 grams of C12. Moles allow chemists to compare amounts of two different substances. 6.02 times 10 to the power of 23 equals Avogadro's number. So one way to measure a substance is to count the amount of particles within a substance, so each individual particle. So for example, if I want to measure the amount of dirt here, I can count each individual particle of dirt, each individual piece of dirt, right? But that is relatively impossible because there's so much and because it's so tiny. Therefore, what I can do, I can introduce a term, right? I can introduce a term that represents a specific amount of dirt. For example, a handful, one whole handful of dirt. So that is similar to a mole, right? A mole represents a term, a specific amount of particles within a substance. This pizza, right? How much would this sausage by mass take up within the pizza, right? So that is basically a percent composition. We're trying to find out how much does an element take up in the compound by mass, right? So for example, if we have here phosphoric acid, we're trying to calculate the percent composition by mass of hydrogen, phosphorus, and oxygen within phosphoric acid, right? So how much mass do they contribute to the compound? We start by finding the molar mass. For hydrogen, that's 1.01 grams per mole. Phosphorus, 30.1 grams per mole. Oxygen, 16 grams per mole. As we can see here in this compound, there's 3 hydrogens, right? So 3 hydrogens, therefore we say it will be times 3 to equal 3.03. So the mass of hydrogen within phosphoric acid is 3.03 grams per mole. The next one, phosphorus, right? Times 3. And we have right, so phosphorus, right? As you can see here, there's only one phosphorus atom within phosphoric acid, right? So what we can do to it is just times 1. One phosphorus atom, that's 30.1 grams per mole within one molecule of phosphoric acid. The next one, oxygen, right? There is 4 oxygen atoms within one molecule of phosphoric acid. So you do times 4. And the answer is 64.0. 64.0 grams per mole of oxygen within phosphoric acid. And now to find the total mass of phosphoric acid, we add them all up. So we add all of this will be added. So the mass of hydrogen, phosphorus, and oxygen. And the grand total is 97.13 grams per mole. That is the mass of phosphoric acid. Now, the molar mass of phosphoric acid. Now, to find the percent composition, basically we're going to divide the hydrogen and the total molar mass. Molar mass. We're going to find it. We're going to take phosphorus and divide it by the total molar mass. We're going to take oxygen and divide it by the total molar mass. And that will be and from that we'll be able to find the percent composition of each individual element within phosphoric acid. So for example, so we can start by using hydrogen, right? So hydrogen is 3.03 divided by 97.13.
Empirical formula, there's 4 steps we're going to use. First, we have to assume we have 100 grams of the compound. Second, we calculate the number of moles. Third, we divide by the smallest number of moles, and then we multiply until whole. So let's say we have a compound with 74% carbon, 8.65% hydrogen, and 17.3% nitrogen. So we're using our formula moles equals mass over molar mass. We assume that we have 100 grams of the compound, which means 74 grams of carbon, 8.65 grams of hydrogen, and 17.3 grams of nitrogen, and then divide by their molar masses. So dividing these, we get 6.17, 8.65, and 1.23. We're then going to divide each of these by the smallest number of moles, which is nitrogen, 1.23. And this gives us 5, 7, and 1. Therefore, the empirical formula of this compound is C5H7N. And that is how you calculate the empirical formula of a compound.
Hello ladies and gentlemen, my name's Adam, and welcome to my laboratories. Now today, the experiment will not be taking place in that thing behind me. Actually, no experiments will be taking place. I'm just going to talk about moles and the application of the concept of moles that you have already learned previously to solutions and acids and bases. So there are a couple concepts I want to cover with you. The first one being about concentration. Now I have this acid with me. We're not going to do anything with it. It's hydrochloric acid in a 10 molar concentration. Now what that means is there are 10 moles of solute, being hydrogen chloride in this case, dissolved in the 1 liter or 1 decimeter cubed of water, which is the solvent in this case. What can you do with that? Well, we have this beautiful equation called N equals CV, where it relates the number of moles in a solution to the concentration of the solution multiplied by the volume of the solution. So you can do lots of things with that. You can find one if you have the other two, and it really helps in the lab. Try to, do lots of stuff, make reactions. Also, from that you can find the C1 multiplied by V1 is equal to C2 multiplied by V2. That helps you dilute solutions, because you don't want to be using this 10 molar stuff to, do experiments in the lab, because that's a little dangerous. Other stuff you could do with that. Yeah. Limiting and excess reagents. I don't know. Lots of stuff in the lab. Titration, very good for that too. Know the number of moles in whatever solution you're using. Know the concentration. And you can find the missing concentration by the little drops with the indicator in there. Second thing I want to talk about is pH, the power of the hydronium atom. So when this thing dissolves in water, since it's a monoprotic acid, it dissolves at a 1-to-1 ratio of hydronium atoms to the actual hydrogen chloride. So that does is you plug it into this wonderful equation where the pH is equal to the negative log base 10 of the hydronium atom concentration, which is in this case is 10. And that's always in moles per decimeter squared, molar, which is why it's important, which is what I'm talking about. So that gives you -1, which is actually very, 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 very acidic. Stuff usually ain't that acidic, but it's very acidic. So yeah, there you go. You could do the same thing, POH with bases. And that's it. I don't think I can talk about much more without stepping on other people's subjects. So there you go. Moles and solutions, acids and bases. Fun stuff. Signing off.